Okay, now we are talking about the work and energy in electrostatic. So we are trying to talk about what is energy stored in the electric field. So let's get started. Okay, so now, uh, so because we need to take energy to place the charge to space. If there is some force, there must be some energy. And when we move the charge from very far to certain place with electric field, we have to do works. So that will give the energy stored in this process. So a certain charge distribution Qi give field in space. Moving a test charge Q capital Q from A to B need to do works. So work by definition is the force in a product with the displacement S. So in other words, this was the very basic one. So we are continuous to having this process. So we would do the path integral for the force inner product with the path. So we take everything together. So there'll be the total work done. So the force applied on the test charge is force times the charge times the electric field. So by this thing, we will write down the total work is actually the work done is from A to B, and it take the energy is the QE, which is the force in the product with the path. Then, because the electric field is just simply the force electric field times path integral with the path. So we'll get a potential. So essentially, by combining these two, we know the total work done is the charge times the potential on the places, which is the location A and location B. So the potential difference times the charge will be the work done. By moving charge from point A to point B, it's just the difference of the potential according to the location. So now, or the potential is the difference between the work divided by the charge. So consider moving the test charge from infinite, where potential is zero, also set B as R. So now we actually have a location initial from infinite, which is potential, we set it as zero. So we set the location of B is R. So we now have the total work from infinite, bringing a test charge to a location R. So there should be it. So what can be directly calculated by just potential. So that's also another reason why we want potential. So evaluate the total work done by assembling a charge distribution. So typically we can consider a process. We bring charge one by one from the infinite to the exact location they are distributed. So we just one by one adding up the total work. So the process is the first charge, we move the first charge to certain location. No work is needed because initially there's no electric field. But when we move the second charge, the work done from the infinite to the location of the second charge. So here we noted that the charge, we write it at Q2, but the distance that we need to consider is the distance between the first charge and second charge. So this is funny R12, funny R12. So the field is uh, given by the first charge. So that's why moving the second charge to the location, it takes this much of energy or the work need to be done. So then the third charge is influenced by the first charge and second charge. So we write things down like this. So the distance is corresponding to first to third, second to third, like that. So go on and we can continue. And the total work done is just been summed like this one. So this is pretty much just like counting each individual charge and inference the incoming new charge. So how much energy is needed. So more generally, we just writing down so we can have the first charge to the nth charge, and the energy is the the each individual charge need to be considered. So it's from the j is larger than I to n is the total number of the charge you have in this system. So in that case, we can also do the same thing, but as long as I equal not equal to j, we just write things down. But because of the in this case, we counted twice because ij and ji will be counted the same, and the distance is the same. So we counted twice, so we divide by 2. That's pretty much it. So we write things down. This will be the total work done, or more precisely, is half of the ice charge with that potential is that position. Okay, so in other words, the total energy is stored in the configuration or the arrangement of the charge. So by sitting there, they have energy there. So it's stored in the configuration or how you set up the charge. Okay, now this is the discontinuous form or the discrete charge form. So take it as a continuous, we're just replacing the charge into the charge density and potential, write down the potential function. So we just take the integration through the entire space. We can have the total work done. So similarly for the surface line charge distribution is all the same. Okay, now, so by consider what we have in Gauss law, and we just rewrite the entire thing by replacing uh, the charge distribution or charge density into the electric field. So we write things down like that. And of course, we know the potential and the electric field are related. And within the identity in vector calculus, we just can replace it, and we replace it just as it is. So now our work can be represented in the electric field and the potential. So with that, several steps after that, we figure out that the total work done by using all the identity we have has something like this one. And that give us some interesting thing. So the electric field square actually related to the work. Okay, and there's another line integral, but anyway, we'll see it. So the thing is, these two terms, this one is actually corresponding to the volume is the volume that we have the charge. So no, not just the charge over the old charge, but actually it can be considered in the entire space. Okay, so the integration is the electric field square integrated through the entire phase will equivalent to the work done by assembling the charge into certain configuration. Okay, and the second part is the surface integral, and with a closed surface where the electric field everywhere and the potential everywhere taking the inner product on the surface. So here we just trying to do a little trick. So this surface is the same volume, but just the outer outer surface of this volume. Okay, so now let's take a look at it. For the electric field is pretty much proportional to the distance square, 1 over distance square, and the potential is proportional to 1 over distance. So, and the area we try to integrate, which is we are trying to get rid of this term. So that is the area of the exterior of the volume. Okay, so by taking that, this thing is proportional to the r square. So because the surface area of assuming it's just a sphere, for pi r squared, that kind of thing. So it's proportional to r squared. So if the volume is bigger and the area will be bigger, but the volume is proportional mostly r cubed, but This one is proportional to r squared because it's the area. Okay, so now this term, take a look at it. It has a voltage. I'm sorry. It has a potential. It has the electric field. So it will be 1 over r, 1 over r squared. Okay, and this is the area 1 over r squared. So the entire thing have the unit in 1 over r. So now we can consider if we choose the volume to infinite large, so the entire space, because the volume is somewhere where we choose. So now we choose the volume is the entire space. So now the R almost infinite. So in other words, if we consider the entire space, this term will turn into zero. In other words, this original formulation that the totally work done by bringing a charge into the certain location as the configuration we have of the charge, we have the total energy or the work done equal this. And that is the interesting thing because the total energy is actually the electric field squared all over the volume you have. In other words, the energy is stored in the electric field. Okay. Okay, from definition, originally, the work done is by the charge and the potential and taking the volume integral or the surface integral. And the potential at the surface of the shell can be written something like this one. Okay, so uh, the work done will be something like this one. Okay, so that is the sorry, this is the example 2.9. So the energy of a uniformly charged spherical shape shell with radius r. So you bring in everything, so you can use the definition of all the work done. That is the location of the charge and times the potential everywhere, and we can rewrite it into the surface form, surface integral. So there will be the same thing. So the potential at the surface of a shell, which is given earlier in previous example. So the total work done will be something like this. And we can use the electric field square as that. So inside the sphere, the electric field is zero. Outside the sphere is just like equivalent to a charge located at the center. So by that, we just take the integral of the electric field outside the sphere. With that, we can just doing the just some mathematics. So we just derive it, and eventually we'll got the same result. This is the work you have to be you have to offer to assemble this spherical shell. It's the same thing. Either you use the fundamental definition or just use the electric field square. It's the same thing. Okay. So now the comments on electrostatic energy. So here the work done uh, is electric field square. So it's always positive. So you always need to do work to make the assembly. Yeah. And well, then on the other side, the energy or the work that's been done is the charge times the local potential. And in this case, the charge can be positive and negative. So energy can be positive or negative. So what's the energy of a single charge? So that become a problem because this result probably doesn't add up. So if we consider we have a charge, so how much energy of a single charge? Because a single charge by itself it has some problem because the electric charge by itself is a point. So that we can write things down, the electric field, the charge like this. And if we really take the volume integral, we will go over the charge itself. And the distance in the vicinity, in the very nearby location of a charge is infinitely close and the energy will be infinitely large. So assembling a point charge requires infinite amount of energy. So that becomes a real problem. So this is eventually lead to the discussion in quantum electrodynamics. So that becomes something way above the topic we are talking about here. Okay, so these equations are correct, just different way to use them. The electric field integration is the complete form considering all energy, including constructing a single charge. The potential sum one is for assembly the configuration. So here we don't talk about how we put the charge together, but this one is all included. But when you use it, we have to be a little bit aware about what's happening here, but not too much of a problem for classical use. We just consider you already assemble the charge. You don't consider how much charge itself has the energy. Okay, where is the energy stored? Like we said, is it in a field or in a charge? Okay, in this one, it seems like the energy is stored in the field itself. And this one, it seems like the location of the charge store the energy. For later discussion of electromagnetic radiation, we tend to consider the energy is stored in the field because later on for electromagnetic radiation or light wave, there's no charge. So only the field. So at that time, we will not consider charge store energy because there's no charge in vacuum in free space. So we'll say the energy is actually stored in the field. And hereby, by that, we just have a very quick look. So that is the energy stored in space. And consider the unit. This thing is a joule, which is the unit of energy. And like this one is actually taking the volume integral into the energy. So this is joule. So uh, so this electric field square times this epsilon naught divided by 2 has the unit of joule divided by length cube or meters cube. So this can also be considered, we will name it energy density, is how much energy in the unit volume. So that's unit and the energy density. Okay, so keep going. Energy is proportional to electric field square. Therefore, superposition energy is not the case. So if electric field equal E1 plus E2, so our total work is electric field squared. So when we rewrite the total electric field into the component E1 and E2 and taking a square, so you have originally E1 and E2, which can be written down as W1 and W2, but there's some additional cross term, which is E1 and E2, their product. So that cannot be just using the superposition as we did before for electric field. So need to be very careful. Electric field potential, they can be superposition, but energy is not in this case. Okay.